This is unit 4.3. The practice, let's get into it. A store is having a 12-hour sale. The number of shoppers who have entered the store t hours after the sale begins is modeled by this function. From 0 is less than t, which is less than or equal to 12. At what rate are the shoppers entering the store 5 hours after the start of the sale? So we're trying to find the rate of change of the number of shoppers entering the store at t equals 5. So to do this, all we got to do is find the instantaneous, we're finding the instantaneous rate of change at 5 hours. So we can just take the derivative of this and plug in 5. And this unit is actually entirely calculator based. So you can plug this into, you can do this on your calculator and you should get 200. And then for the units, well, our independent variable is the number of hours. We're going to take what's plugging into t, or what's in the parentheses, which is t, which is represented of the number of hours, and then our dependent variable is what E represents, which we can see is the total number of shoppers. So it's going to be our independent, which is hours, our dependent, which is shoppers, per our independent, which is hours. So shoppers per hour. And that's our answer. Question 2 says a function modeled p, f of p models the time and days for a small pond to evaporate as a function of the size p of the pond measured in liters. What is the unit of f double prime of p? So now, first let's find our independent and dependent. Our independent is what's in the parentheses, so the p, we see that p represents the liters of the pond, so that's what p is. That's our independent variable. Our dependent variable is what the function represents, which is the time in days. So it's going to be our dependent per our independent, so days per liters. So I'm just going to write that down, days per liters. And it's asking for f double prime of p. So this is f prime of p. This is the unit for f prime of p. For f double prime of p, we're going to take the rate of this, which is just days per liters, or days per liter squared. So I hope that made sense. The temperature in degrees Fahrenheit of a lake is a differentiable function, W of time t. The table above shows the water temperature as recorded every 5 days over a 20-day period. Using the data from the table, find an approximation of W prime of 10. Show the computations that lead to your answer. Indicates the units of measurements. Okay, so for this question, we need to find the rate of change at 10. So to estimate that, we can just take 2 points around 10, so this point, and find the slope between them, and that will give us a good estimate for the exact instantaneous rate of change at 10, which is W prime of 10. So y2 minus y1 over x2 minus x1, so we have 64 minus 60 over 15 minus 5. 64 minus 60 is 4, 15 minus 5 is 10, which is also 0.4 in decimal. And our units, well, our dependent variable is degrees Fahrenheit, our independent variable is days, so it's degrees Fahrenheit per day. So there we go. That's our answer. Alright, the function 13 minus 2.7 cosine of pi over 4t models the depth in feet of water t hours after 6 a.m. Find the instantaneous rate of change of the depth of water at 9 a.m. Use appropriate units. So now for this one, we're just finding the rate of change of this function, instantaneous rate of change of this function. So we just take the derivative and plug in a number. Now we need to find what t is. What's the number we're plugging in? So we want to find the instantaneous rate of change at 9 a.m. and t is the hours after 6 a.m. So 9 a.m. is 3 hours after 6 a.m. So that means t is going to be equal to 3. So we take the derivative of this and we plug in 3. We can do that on our calculator, and we should get an answer of 1.499. And then our it's dependent per our independent. So our independent is what t represents. T represents hours after 6 a.m. And our dependent is what d of t represents, which is the depth in feet. So it's going to be our dependent, which is feet, per our independent, which is hours, so feet per hour. That's our answer. The rate of consumption of liquid chocolate in Switzerland is given by R of t equals CE to the KT power, where R is measured in millions of gallons per year, and T is measured in years from the beginning of 1990. The consumption rate doubles every 9 years. and the consumption rate at the beginning of 1990 was 2 million gallons per year. Find C and K. So, let's dissect the information we know. Let's start with our first piece of information. The consumption rate doubles every 9 years. That means that if our original function is C e k of t, when we plug in 9, that should be equal to 2 times when we plug in 0. So that should be equal to 2 times C e k at the original, which is 0. So let's simplify this down a bit. We get 2c, k times 0 is 0, e to the power of 0 is 1, so it's just 2c, and then e to the power of k9, we can't really simplify that, so we get c e to the k9 power. We can divide both sides by c here, so we get 2 equals e to the 9k power. And to solve for k here, we just take the natural log of both sides, so we get ln2 equals 9k, and then we divide both sides by 9, so we get k equals ln2 over 9. Now, if we plug that into our calculator, because this is calculator, we get about 0.077 is our k value. So now for our c value, let's use our second piece of information. The consumption rate at the beginning of 1990 was 2 million gallons per year. So what does that mean? That means at the beginning of 1990, if t is the number of years from the beginning of 1990, that means at the beginning of 1990, t will be 0. So we want to find r. So this information is telling us that r of 0 equals 2 million. And remember, r is measured in millions of gallons, so r of 0 equals 2. So r of 0 is just c e k to the 0th power, so let's go ahead and write that down. K times 0, and then we know that's equal to 2. So k times 0 is 0, e to the 0th power is just 1, c times 1 is just c, so that means c is equal to 2 as our second answer. So these are our two answers. Let's move on. The temperature of water in a bathtub is modeled at time t is modeled by a strictly decreasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. The water is cooling for 30 minutes, beginning at time t equals 0. Values of w of t at selected times t are given in the table above. Use the data to estimate w prime of 15. Show computations that led to your answer. Using correct units, interpret the meaning of your answer in the context of the problem. Alright, so first let's do the first question, which is use the data in the table to estimate w prime of 15. So 15 would be about right here. So we can just use 2 points around it and find the slope between those to estimate the instantaneous rate of 15. So I'm going to use this point, and I'm going to use this point, which is right around 15. y2 minus y1 is 79 minus 90. That's the 9 out of 4. Over 20 minus 10. And that's going to be equal to negative 11 over 10, which is equal to negative 1.1. And then as for our units, it's our dependent per our independent. Our dependent, so w of t is degrees Fahrenheit, and then minutes, so dependent per independent is degrees Fahrenheit per minute. So degrees Fahrenheit per minute. There we go. Okay, so now the next part of the question is using correct units, interpret the meaning of your answer in the context of this problem. So I'm going to say at 15 minutes, or what does it say? T is the measured in minutes. Okay, so at 15 minutes, the temperature of the water is decreasing at a rate of 1.1 degrees Fahrenheit per minute. And that's a good answer. All right. Next question. Approximate r prime. The rate of decay in grams per minute of a radioactive substance is a differentiable decreasing function r of time t in minutes. The table below shows the decay rate as recorded every 4 minutes over a 24-minute period. Approximate r prime of 12. So 12 is right here. So I'm going to use 2 points around 12, just like we've been doing. So y2 minus y1, 39 minus 130 over 16 minus 8. And of course, you can just plug this into your calculator to get about, what is that? Okay, let me do it in my head. 3 minus 136. 1, 121. So that's like negative what? 11.375. 375. I hope that's right. And now our units is our dependent per our independent. So grams per minute, or we can rewrite that as grams per minute squared. So both of those the same thing. It's squared because we're taking the rate of a rate of change. But yes, a physicist proposes a function, this new function, for a model, we need to find g prime of 12. So we can just do that on our calculator. Just take the derivative of this and plug in 12 on our calculator. You should get about negative 8.905 grams per minute. And remember, it's squared because we're using the same units as r of t, so we're just copying that down. So grams per minute squared. And then for our explain the meaning, all we gotta say is at 12 minutes this is modeling the rate of decay, so the grams of a radioactive substance, oh my gosh, I can't spell, is decreasing at a rate of negative 8.905. Or actually, wait, this is the rate of a rate, so we should probably say, how do I edit? I'm just going to delete it. We should probably say the rate of decay of a radioactive substance is decreasing at a rate of negative 8.905 grams per min squared. And that's a good answer. Alright, next question. For time t is less than or equal to 0, greater than or equal to 0, let this be a function that represents the speed in miles per hour at which the car travels. Find r prime of 2. You can do that on a calculator, so we get 8.513, and then it's our dependent per our independent. This is our function which represents the speed in miles per hour, and t is hours. So it's actually, our dependent variable is miles per hour, so mph, and then our independent, which is per hour, or we can write that as mph squared as our final answer. Alright, moving on to the test prep. People are entering a museum at a rate modeled by f of t people per hour and exiting the building modeled at g of t people per hour, where t is measured in hours. The function f and g are non-negative and differentiable for all time t. Which of the following inequalities indicates the rate of change of the number of people in the building is decreasing? Alright, so the number of people in the building can be calculated by the people entering minus the people that are leaving. So the number of people in the building can be modeled by f of t minus g of t, right? So then when it's decreasing, the derivative is less than 0, so we just take the derivative of this and set it less than 0. So f prime of t minus g prime of t is less than 0, and that's our answer, which is answer choice D. Alright, this one requires a calculator. This is the rate, let me read the question. The rate of R of t of a certain item produced in a factory is given by this, where t is the number of hours since the beginning of the workday at 8 a.m. At what time is the rate of the production most rapid? So we need to actually graph the derivative, and we need to look at the graph and see where it's at its maximum. Okay, so first let's just take the derivative. So we get, I'm going to do this without a calculator. You can do this. If you do this on your calculator, you can't use x, you have to use t, and then at the end it's going to say t equals, so it's going to look like this. You're going to have d over, and you have to put dt, and then you have to put write out this entire function, and then at the end it says x or t, it's going to say t equals, and you have to put t equals x, and you type that into y1, and then you can see the graph. I'm just going to tell you what the derivative is. That's 48 minus 12, and then chain rule with t minus 3 squared. Right? Yeah, that's correct. Yes. Right? Yeah. Okay. So yeah, go ahead and graph that. You should have a maximum at t equals 3, which is, so 3 hours after 8 a.m. is 11 a.m. So that's our final answer. Anyways, thanks for watching. I'll see you in unit 4.4.